Welcome back, class. This series of videos is going to help prepare you for Test 4, which is going to be on Friday, October 30th, and is going to cover sections 3.1, 3.2, 3.3, and 3.4. So what are we going to be talking about this week? We're going to be talking about this thing we have previously alluded to, namely the instantaneous rate of change. And as we're going to call that, the derivative at a point. So I want to remind you where this came up before, to start with, and then talk about how we're going to interpret this question in this section, and then go from there. So we've got this function, y equals x squared, or f of x equals x squared, I guess I'll say. And we've got some input, and the last time I did this it was 4, so I'll do it with 4 again. And we want to talk about what the slope of the graph is at this point. Note that already, when I say the slope of the graph at this point, we have to do a little bit of interpretation of what it is we actually mean. And so what is it we really mean? We really mean the slope of the tangent line at that point. And so if we drew in this dashed line here that was tangent to the graph, then that slope would tell me the slope of this graph at this point. But notice that slope would be different if I were over at some point, say here, and I drew in a tangent line, and it would look like this. This line has a totally different slope than this one. Okay. And that's why this is called the instantaneous rate of change at the point. And this is called the instantaneous rate of change because it's the rate of change, or the slope, at a particular instant. And at every other instant, there's also an instantaneous rate of change, but it's a different instantaneous rate of change. So the slope here is different than the slope here, is different than the slope over here, and so on. Okay. So all of these phrases are different ways to say the same thing. The slope of the graph at a point, the slope of the tangent line to the graph at that point, or the instantaneous rate of change. All of these things are different ways to communicate the same idea. Now, we'd like to be able to talk about this more concisely, and so the notation we're going to use, if I'm talking about the slope of the graph at that point, is I'm going to write this as f prime of 4. So this apostrophe I am reading as prime. Okay. And so the advantage of this notation is that it is infinitely shorter to describe than all of these other things. And so the slope of the graph at this point, or the instantaneous rate of change, the slope of the tangent line, any of these different things, I'm going to write all of those by f prime of 4. Okay. The f is because this function is f. And the 4 is because that's the point on the graph that I'm looking at. That's the input where I'm talking about this. Okay. And then the prime here stands for our last word for this, which is the derivative. And so you could read this out loud as f prime of 4, or you could read it out loud as the derivative of f of x at 4, whichever way you want. But importantly, all of these different phrases are communicating the same thing. How are we going to calculate this, though? This is supposed to be the slope of the tangent line, and you might recall there was some complication with the idea of the slope of the tangent line. Okay. But what was never very complicated was the slope of a secant line. And so I'm going to draw in a secant line here. The slope of this secant line we know how to calculate as soon as I label this point. Okay. So this point here, it is 4, 16. The 16 is because 16 is 4 squared. And I'm going to go ahead and I'm going to decide that the gap here, I'm going to go ahead and label as h. So this gap here is little h. And since this gap is little h, that means that this input here is 4 plus little h. And that means that this point here is 4 plus little h, comma, 4 plus little h all squared. And so the slope of the secant line between 416 and 4 plus h, comma, 4 plus h squared, I can write down. It's going to be 4 plus h squared minus 16 divided by 4 plus h minus 4. Okay. Which I'm going to go ahead and take this time to do a little bit of algebra to simplify that. Namely, that is going to be 16 plus 8h plus h squared minus 16 divided by, and then the 4's are going to cancel, so I'm just going to get divided by h. So this is going to be 8h plus h squared divided by h. I'm going to factor the h out. And I'm going to cancel the h's, and so this will be 8 plus h. And so what does this say? What this says is, if I choose this gap to be h wide, then the slope of the secant line that I drew in here is 8 plus h. So for example, if h was 1, this would be talking about the secant line through the inputs 4 and 5. Or, to harken back to our previous terminology, that would be the average rate of change of this function between 4 and 5. Or, if I chose h to be 6, then this would be 12, and that would be the average rate of change between 4 and 10. But remember, what I'm looking for now is I'm looking for the instantaneous rate of change. Namely, I want this interval to be as small as possible. Okay. Namely, I really want to think here about this h being 0. Okay. And so my instantaneous rate of change here is going to be just what I get out of this formula when h is 0. So it is just going to be 8. Again, what is h equals 0 saying? H equals 0 is saying I'm really taking the average rate of change over the interval from 4 to 4. That is, I'm really taking the instantaneous rate of change at exactly the moment 4. Now, unless you paid very close attention, you might not have noticed that I just cheated there a little bit. Namely, where did I cheat? Well, I wrote down this whole business, and then I plugged in h as 0. But what would have happened if I'd plugged in h as 0 at the beginning? Well, if I'd plugged in h was 0 at the beginning, then I would have been finding the slope of the line between 416 and 416. And so this would have been 0 over 0. And so this would have been undefined. So what did I really do here? I really calculated a limit without using the word limit. So let me rephrase this using the word limit where I'm supposed to. So here's what's going on. F prime of 4, here's what we really said, if you look back at this previous page. F prime of 4, that is the instantaneous rate of change at the moment 4. It's the limit as h goes to 0 of the average rate of change between the point 416 and the point 4 plus h squared. Now, I couldn't just plug in h equals 0 here because that would give me between the point 416 and 416, so that doesn't work. But I can calculate this limit. And indeed, we did calculate this limit, and we found that that limit is 8. I mentioned before that this idea of finding the slope of the graph at a point is something that took people thousands of years to really make sense of. And the reason why it really took people thousands of years to make sense of is because you can't just plug in h equals 0. That makes no sense. You have to use this weird idea of limits that we talked about last week in order to make sense of this whole story. Now, let's write out the general version of this. So for a general function, f of x, what is f prime of a? So for a general function or an arbitrary function, that is just for some random function f of x, what is the slope of the graph at the input a? Or what is f prime of a? Well, it's equal to the limit as h goes to 0 of the slope of the line between a f of a. Okay, so this is our point that's playing the role that was played by 416 before. This is the moment in time that we're looking at. And then a plus h, f of a plus h. Okay, so this is saying if I move to the right by h, what point on the graph do I end up with? Okay, but then I have to get rid of the h, and the way I get rid of the h is by taking the limit as h goes to 0. Now, I think it may very well be the case that this is the nicest way for you to think of this formula. But if you don't like this way, or if you want this spelled out a little bit more, we can write out what this slope is. Namely, this slope is f of a plus h minus f of a divided by a plus h minus a, but a plus h minus a, that's just h. And so when we go to calculate derivatives in the future, we can go straight either to this line or to this line. Okay, we're going to talk a lot about what these derivatives mean in the next section, that is in 3.2. For the rest of this section, though, I just want to focus on doing the raw calculation to get one of these things. We're going to stop this video here. In the next video, we're going to hop into calculating some derivatives using these formulas. But that's all for now. I'll see you next time.